Can you recall the slide number properly? Okay. Yes, I think I was in this slide, right?
Yes, sir. Yes, sir.
Fair enough. So let's start again. Sorry for your inconvenience yesterday. So what I wanted to say, we have a technology that is quite old, that is the lead acid battery, and that is not environmental friendly one. And for this reason, we are gradually phasing out it. And, gradually we are looking towards the metal halides and the lithium ion. So these are the two batteries that is having a great importance nowadays. However, it has the challenges. That is something we require to focus and require to address it. So, one aspect is that high cost of the nickel metals, what happened, and another aspect that if someone wanted to make the nickel metal halides, they have to get permissions from this atomic group, so that, because metals are used as a strategic material for the nuclear power. So nickel is not being traded in a normal way. So that is one of the reasons, and it has been licensed or rationing has been done how much nickel metal you can use. And thereafter, that is one of the challenge. And high heat generation is a challenge. And heat generation, that means that you require a proper cooling system and control uses of the hydrogens or the low cell efficiency. That is also the challenge. Now, for this reason, we have a lithium-ion batteries that is quite frequently been used nowadays. You have laptops and mobiles; these are all, and we are looking for the lithium-ion battery. One of the major disadvantages of the lithium-ion battery is that energy density is not so high like a nickel metal hydride. And another aspect is that the abuse tolerant. That means if the car is subjected to the collision, then how we can proceed. So how you can actually make that system the resistance proof. That typical case came when the dim liner. So that has been using this kind of battery some extent, but they have a patent. So for this, they don't disclose everything. So those issues was popped in. So ultimately, dim liner has to be grounded. Perhaps you recall. So these are the few aspects of the battery. We have to keep it in mind. While doing it, we have to take the cognizance of the e-vehicles. Okay. So this is one of the examples of the. Now we talk about the ultra capacitors. As I actually said, we have missed out this slide, I think. So ultra capacitor is mainly for the transient, because it has been seen that 30 to 40% energy is been lost in braking. So while braking, it is not possible to reverse the directions of the direction of the current, because you have a inductor into the system and other issues. And then what happened, and you have to reverse the chemical process into the battery. If it was charging, then it is discharging. So that takes, that chemical time constant is a couple of seconds. But within that couple of seconds, you are going to stop the car. So for this reason, it is, you say that, yes, I make the current direction reverse. The moment your current direction reverse, that will give us just a spikes for the SOCs. So for this reason, what happened, this extra, this braking energy can be stored into the ultra capacitors. And thus, you can increase the efficiency of the motor. And of course, there is a challenge. Challenge is that when we were learning physics in our plus 2 level, we are being Faraday's law. So Faraday's law. So we have been told that, to require one capacitor of 1 farad, we require the dimensions more. We require the dimensions more than the earth. But anyway, nowadays, because you go by a simple principle, and we have the polymers that can sustain the high electric field, and that can give you hundreds or thousands farad capacitor within a reasonable size. So that is one of the great features, and that help us to increase the efficiency of the motor. Now, talk about the energy storage flywheel. Flywheel, of course, it is not possible for the electric vehicle, but it is highly possible in case of the grid connected electric vehicle. For example, I know a case in Delhi. They had a power fluctuation around 10 years ago. So for this reason, they required to put the diesel generator on with a 30% loading for the peak hours. And due to that, there is a huge voltage sag. Ultimately, those machines came from the Hitachi, and those voltage sags was not allowed, so that motor rakes get strips. So there, ultimately the solution, few substations, they put the flywheels, and they try to mitigate the voltage fluctuations and voltage sags mainly. So these can be used for the grid connected urban locomotive system, where you have a huge space, you can store it, but this is also a challenge in an urban area. So this sake of time, I am actually cut short this discussions right now. Now, one important aspect that I talked about the energy storage. Of course, this is associated with the braking. We require to make the system regenerative. Then only those energy storage can be used. So there is a data I was just pointing out. Toyota Prius was one of the pioneer electric vehicles that comes in early 2000. 95 around that time was available into the market, and it has been seen that around 30% of the heat of the kinetic energy is due to the braking. So that efficiency we require to trap it, and that will also reduce our cooling effort, and also we can use it for the useful energy. So that is the case. Now we talk about the fault tolerance. That is a very important part of the today's topic. That is the electrical motors failures, sensors failures, power inverters failures, and the battery management system. I will touch it because it is a whole system is based on that. So we will just touch upon it. Motor have a lot of failures. So let us talk about that first. That fault tolerant control for the EV. So that is the intermittent sensor connections. You may have the encoder. All of a sudden, that encoder goes off, and you miss some pulses by some reasons, maybe due to the mechanical obstructions, and thereafter again you get the pulses, and thus instead of that you measure the speed little low, around 20% or 30% low, and thus you assume that if you are working in a constant torque region for the PMSM machines, so speed can be increased. So you give that command to increase the torque. Ultimately, you go to the saturation level, because you know that if you are using the PMSM, once you go to the higher torque, higher speed region, then you have to apply one control called MPTA. So you have to give that D-axis current negative. So control mechanism totally changes. But since you thought that yes, I am in a constant torque region, let's apply it. So you will be the operator may be in the soup. So another is that complete sensor outage. So that is not dangerous as such. When you see that there is no sensors working fine, you shut it down, then you repair everything. But First one is quite disadvantageous, that gives you the fake informations. Another aspect is that DC bias in sensor management. So some aspects, so that biasing. So and since the sensors are all digital, I just giving an example for but though these are quite complicated one. So we have a point 0 to 0.4 volt. You take it as a 0. If you have a 0 shift, and ultimately the 0 comes out to be 2 volt, then ultimately it will be taken as a forbidden bit. So thus it will not try to interfere. Thus it can be actually difficult to communicate the actual informations. Another is the sensors gain drop. We find is quite. Most of the analog circuits. What happens? Sensors can generate voltage in terms of the millivolt and current in terms of the microamperes. Mostly. So ultimately you have a power amplifier, mostly the signal level amplifier. These are op amps, the high precision op amps. And thus, if some extent that gain of this op amp changes due to this resistance and other networks of decaying, then sensors gain will be a great sufferer, and that kind of problem we have noticed in case of the analog based drive system. And for this reason we say always which cross check with the softwares, and software generally gives you the hardware results in a digital domain, and there you can get a better results. Now let's talk about the machines that been used. Tesla still uses the induction machines, so we require to talk about the induction machines. So it may be that due to the rotation, the axis has been little skewed. If it is little skewed, then its torque performance and the current curve, we have to see it. It is maybe a failure, but it is a problem of the diagnostics. And thereafter, you got a permanent magnet synchronous motor that because of its high torque to inertia ratio, it has been preferred. And you got a switch reluctance motor. We have only the EVAC, of the soft iron, and thus it doesn't have any winding. So for this reason, it is a great advantage. Now, what does this failure relates to? It can be the work designing. What I am mentioning that your axis is little skewed. So and it may be that due to this longer durations of the hour, the axis becomes skewed because of the centrifugal force. And weak dimension lead to the permanent degradations because little skewing of the motor will overhaul a particular zone, and thus the rotor may go. It may ultimately get broken. That is called the broken rotor, and the failure due to the exploitations. That is a car suffered a collisions or intentional damage. And thereafter, this is the mechanical part of it, and you can have a same way or the electrical way. So the frequent overload of it, you it can have a capability of the 1010, you overload it to some other level. And violent transient and severe environment conditions. So like you have a bumpy road and you don't bother to actually take the proper precaution of reducing speed and all. You take the bumps as it is, the jerking will come into the picture, and there are several heating and the cooling will also cause to the premature degradations of the motor. Now that leads to some failures of the motor. Let us discuss it. One is that is very a common failure, that is winding turn to turn short circuit, and it may happen due to the aging. So what happens, you have varnishes or any kind of insulation depending on the kind of insulation level you are working to. So ultimately after some time, that where varnishes or the insulation breaks down and you have a shorted. As you have shorted the turns, effectively the number of turns get reduced, and thus you have a voltage imbalance into the phases. Another aspect is a winding to winding short circuit. So same way, then the high current will locally flow, and ultimately the voltage developed in a back EMF will be unbalanced in nature. And that from that you can get it from the current signatures. So current and the voltage signature. So and the face-to-face short circuit, that is quite dangerous. High current will flow. Ultimately, you will find that no back EMF is generating. So that is quite dangerous. Also, it may permanently rupture the machines. So that we require to take it once you saw that the current is going high, but there is no load torque. Still, it is again showing the high current, and generally it has a current signatures 180 degree out of phase. And another is open circuit. So then you have a reflected wave, and thus you will find that two other phases having a higher voltage and voltage A to be 0. And sometimes what happens, it is a partially short circuit, that is also there. So we have to see that, whatever rated voltage you get, if it is more than that, it is a typical case of open circuit of a one phase. And thereafter you can have a ground fault, and that is quite dangerous. So high current, high leakage current will flow, and ultimately you can get a balanced system also. Then you may not be incorporated a three-phase system, and ultimately you find that torque is not generated, but ultimately in one phase current is high, and then you got a zero sequence component, and thus we require to locate it and prevent it. So one aspect is that, one challenge is that detections of the fault, that is not also suffice the requirement, also the point of the fault. First, so from the current signatures and the voltage signatures, we require to detect the kind of fault occurred into the machines, and thus you take a corrective actions on it. Now, the control I am just showing you. This is we generally run the nowadays a modern cut system, like we do it into the aircraft, because the simulators runs and checks the every signals, every mechanism of it, then it actually starts it, then you can start the aircraft. Same way, you have a controllers, you have actuators, and fault can be simulated there. If it is not there, that provision will be there, so that in actual fault it occurs, then it can detect. So that the fault may be injected in the actuator, and there can be a component fault. So that's what I was saying. And there can be a fault from the sensors, which I was discussed a little earlier. Ultimately, you have condition monitoring. It will give the condition information. Okay, then you can start. Otherwise, it will actually say to the controller, you correct this, etc. Now, how you actually go for fault tolerant? One of the biggest challenge of the fault tolerant is an electrical machines. If there is a short circuit between the winding, you cannot replace the winding. So you have to get utmost cautious that ultimately, due to the maloperations of your sensors and the inverter, that motor is not dysfunctioned. If it is motor is dysfunction, then you have to open the motor, you have to re-burnish, refabricate everything. It is a quite costly and the time-consuming phenomenon. And for this reason, we provide more reliability and the redundancy on the sensors and the power electronics. So, you got the fault tolerant system, and the key is that redundancy, and thus you got the reliability. Redundancy can be categorized in two parts: the direct hardware. For example, let's say you take an example of the two-level inverter. You got a 2 legs. Instead of that, you gave a 3 legs. So for a single phase, or if it is a 3-phase inverter, you got a 3 legs. You gave another leg extra, 4 legs, so that it will help to cater the need. And in case of the ground zero problem comes, and that zero sequence component also can be taken care of by that. But generally, we don't do that. In the event of the material failure, so software and the hardware redundancy both has to be used. For example, I was taking an example of the software hardware system, and but you can do the same thing with the software. For example, let us say that you are using a flying capacitor multi-level inverter for your drive system. So it has got a lot of redundancy. So you have to, that topology gives you a lot of redundancy. If some capacitor gets shorted, so you have an alternative path to generate that voltage frequency. So that is called the software redundancy. And by putting extra switch, this calls the hardware redundancy. The configuration of the system based on the component management and the fitting algorithm in order to choose between the inputs, and we have to see that properly. Why? Because we require to go for it, and we require to see that it is correcting all the checks that we do. That's in case of the aircraft. Same has to be done for the electrical machines. Now, hardware redundancy, as I was talking about, that hardware redundancy, you have to put more for power electronics. You have to put extra switches or extra legs or extra module. Same way for the sensors, you have to put extra sensors. So, and it is not that it is coming from the single point. It has to come from the large number of points, so that you can check which data is coming from the which sensor or not, and thus in that way you can give the reliability. Now the software redundancy. Software redundancy, as I told you, that example is that you have apply that control for the power electronics, so that it can generate the redundancy within a FPGA program maybe. So you can have an observer and the residual generators. And from let's say A and B phase is coming, C phase is not coming from the sensors. And from that A and B phase, you can infer that phase is healthy, but it is a problem with the sensors. Thus, you can generate by software the C phase by addition and subtractions. So that, or any for this, C phase can be generated by this. So in that way, you can generate those kind of signals or fabricate that signal if you are confirmed that yes, the other part of the system is nice, but there's a problem with the sensors. So that is something you can work with the software redundancy. Now, what are the key issues for the EVs? So charging infrastructure, I'll discuss today. And apart from that, you got a understanding of the battery hazards. That is quite important. It can be because that electric vehicle is actually the moving one. It is not like a standalone system in a microgrid, and you can put it into the ACs. So you require a good cooling system, and 30% of the energy has been lost into the braking, and that converts into the thermals. So battery hazards and the battery management was one of the key area for these electric vehicles. Electric vehicles that addresses the concerns in emergency way, we have to respond to it, and permitting inspections and training the personnels. And one of the challenge we are facing nowadays, people are reluctant to EV because of that educated or a trained personnel, because we are using the IC engine based electric vehicle past 50-60 years. We have all the value chain sets, but there is a very few electrical vehicle technicians available in our country and also in abroad. So let us come to the machines part of it. We have the permanent magnet synchronous motor. So that is the torque. Why we'll go for it? It has got a high torque to power density, and lower. You can read it, so it doesn't require much information because I have to capture two presentations now. So I just just go through it. I think that it doesn't require much explanations. So now let's come to the point that FOC, that is field oriented control of the PMSM. So you know that once we have applied for the field oriented control, the flux and the torque can independently control, and thus what happen, your speed and the voltage, speed and the torque can be also independently controlled in that way. However, it has required the complicated transformations from ABC to TQ, and that depends on the that value comes from the PLL or the phase lock loop. So that is sometimes it may cause concern, and you have to take utmost cautious to it, and you have to align that. We generally go for the rotor field orientations so that it is inherently short circuit protected, and we have to have the alignment proper, otherwise those value will give an error and machine will not properly also. Those who are working on it, they can understand that it is been aligned. So let us come to the block diagram of this machine, of this FOC, proposed FOC. I'll show you the simulation results here for sake of better understanding it. So, you got a speed command. Thereafter, you got a speed controller, and essentially it can be PI controller or any sliding mode control, whatever you want, you have it. So thereafter, you get the IQ star, the reference, the Q vectors, and you generally get ID 0. I was talking, sometime that ID star should be negative. So we when we want to go above the synchronous speed, then we generally put ID star 0, that is called MPTA control method. So then you got now I am keeping this 0 for the unity power factor operation. That is one of the advantage of it. So you can have a unity power factor operation even at a low speed. That means that you are using the efficiency better. Current rating through the conductor will be lower. And then you have another PI controller that generates VQ and VD. And ultimately you have transformations. You sense that currents and transform to the DQ frame. And you also sense the speed. From there you integrate it, you get the theta, and that will use the box transformations, and you got alpha beta, and thus you got a space vector modulation and get a pulses. It can be any level inverter. I just sake of simplicity I have shown you the 2-level inverter. It can be any level inverter depending on the requirement. Now this is the example. You can see that this is a simulated results. This is a preferred speed, that is blue one, and actual speed is a red one, and you can in between I give some jitters. It is almost at very low torque at 1 Newton per meter, and in between I give some jitters, and you can see that it is following very well. And I then increase the speed, and you can see that it is smoothly follows it. Same way, you can see that current is sinusoidal. However, I have not given the information about TST. TST is coming out to be around 9% for the for this 2-level inverter. Now these are the different parameters, that is VA, VB, VC, and similarly the same thing. And for the different parameter, that is theta, omega, I have shown all the simulated results, because generally I show in the DTC the experimental results, because experimental results you see that there is a practical notches into the system. So better understanding it, I just show you the simulation results. So now let us talk about the direct torque control. That is the experimental. I show the experimental result. You know that torque is the torque depends on the flux linkage between the stator and rotor and angle between them, and thus we require to maximize the torque. That is the features. So we want to have this flux in quadratures, and the two Japanese scientists proposed is Takahashi and Naguchi. So one of the advantages of the DTC is that it has got several advantages. No coordination transformation. That is, you have you get integrated theta from there. You get the value, and there's no transformations, less dependency, and the quick transformation response, and the simplified low computational time. So these are the advantage of it. You see that, I just give you an example. This is a simulation results. You reverse this, you reverse essentially the torque. So from positive to negative. So 3 Newton meter to the motoring mode. And you can see that, it can be reversed within the 0.8 millisecond. And accordingly, when you reverse it, so there will be a speed characteristics, and that will come into the picture. However, same phenomena if you want to do by a PI controller based method, so that will take a longer method of 0.8 seconds. Now this is the control block diagram, and you see that it's quite simple. You have a rated torque that from there actually you give the you calculate the actual torque from the lookup table, and thereafter you put it to the comparator. From comparator you generate the switching table. Same way for the stator flux, you estimate the stator flux, but all the quantity you require to estimate from the estimator block. That is one of the challenge, and ultimately based on that you have a fidelity on it. You go for the state vector modulation. We have 6 sectors, and based on that you split the flux hysteresis. It is plus 0 and minus 1, and based on, and you got torque got 1, 2, 3, and flux got 1 and 2. So positive error and negative error. Based on that, you can choose a particular sector. When first error is negative, torque error is also negative, that is in first quadrant, and based on that you will be V2. So accordingly you can see the sectors in a space vectors. I just give you that, I just show you the waveforms. You can see that is the blue reference line is the torque one, and another is actual torque in a spring. So it is quite oscillation. That is because of the hysteresis. So torque will have a more oscillation in hysteresis, and it is a 2-level inverter, and this is a current, and you can find that THD comes out to be 13%. And thus these are the challenges of the DTC. So you have a high torque ripple, and we require to reduce the torque ripple. You have a high THD, and also you got a problem of the not having a constant frequency. So if you design a filter, so that's something also will be challenged, because depending on the load, you will find that frequency spectrum of this current is varying. So you can go for the 3-level NPC, and thus you have a 12 sectors, and you have a 27 space vectors, and based on that you can go for it, and thus you have to generate the sectors like this. For sake of time, I am skipping that part. So please write to me if you have an interest, then I can discuss in detail. So you have a 0 vectors, and from there you can generate a particular sequence, and thus you get into the particular sectors also. And what happened, and thus you can see that from the previous waveform, this waveform has a less torque ripple, current is better, and current THD is around 8%. However, there is a problem of the constant switching frequency. I cannot show you here properly the spectrum. In next slide, in the 5th slide later, I'll show you that how the constant frequency spectrum and this kind of situation appears. So we can conclude easily that because of the 3-level inverter, however you get the complexity, however you reduce the cost in the filters, and also by this reducing the THD, you have enhanced the life cycles of this THD. And how you generate this torque controller, it is quite easy to generate by a hysteresis comparator. I just show you, you got a hysteresis comparator, there you got a NOR gate, and thus you get a conventional torque controller. And we made a one torque controller that you'll be using for the constant frequency operation. So that also helps to reduce the THD at a gate extent, and also you got a constant frequency operation. Thus, your switching spectrum is quite limited, and it is easier to design the filter. So only thing that you require a sawtooth wave, a triangular waveform with a high frequency around 10 kilohertz. So accordingly, when there's a torque error will be there, we have a PI controller. So tuning on a PI controller is a little bit challenging. So otherwise, you can see the results. This is the flowchart of the constant frequency wave operation. This paper has been published recently in IET. It is in a press, so it will be coming in next February, I think. So this is the block diagram of this features, and from there you can see that this is a two-level inverter only. You can have a drastically reduction in switches. Still, you can see that THD is close to 7%, and you got a less torque ripple also. So ultimately, if you go for the constant switching frequency DTC, which we have actually contributed also, so that something have a great advantage over the conventional DTC. Ultimately, this is a frequency spectrum of the first two. This is for the two level. You can see the huge variation, and you can see that spectrum is splitted. And this is for the DTC. You can see that this is the spectrum. This is the spectrum that easier to actually notch down or eliminate those frequencies. Now, one of the disadvantage of this electric vehicle is that we have a problem of the sourcing and the proper designing of this electric vehicle. I am facing a great amount of problem because those permanent magnets are available only. Those permanent magnets are available only in the China and all those countries, and they have taken a control over it, and it is almost a monopoly. And these are all rare earth materials. So these are the huge challenge, and the manufacturability in India, it requires a lot of competence. Unfortunately, it is not met locally. Tata is sourcing from the Korea, so ultimately they have a huge dependency on the South Korean companies. So what happened? So due to the now we go for the SRM as a EV candidate. It has got a rugged structures because that's what I was saying, that no rare earth material is required, and manufacturability is cheap, easy, everything, because you make it with a soft iron due to the independent phase excitation, and it has got an inherent fault tolerant capability, and their rotor do not generate significant amount of the heat. Only problem is that if you rotate it till higher, then there is a problem of the eddy current losses. That we have to see that how to minimize it, resulting in an easy cooling. So operations in higher temperature is also possible, because that is one of the advantage of the electric vehicle. Low torque to inertia ratio. However, since it gives a pulse, so it has also a problem of the higher torque ripple. So features, I don't go to that details. I think you all know the SRM. So that is it has a double silency and is singly excited. It has got a central winding and no permanent magnet or the conductor in the rotor, that makes it compact and the low cost design. So this is the SRM block diagram of it. So you got this kind of circuits. So you can see that there is a diode, and that when followed by there, ultimately you got a omega, and from there the speed command, and circuit is very simple compared to the what we have shown you in the vector control. Then there are the DTC you got, or a lookup table, and from there SRM. It is quite simple to design these circuits. Now you got a control strategies. So generally you go for the current control, torque control, because you have to estimate the torque. So since we can measure the current control, we go to get the current control, and it gives a inherent protections of the short circuit protection. And but it is possible to go for the DTC, and thus you got a greater control over the torque. Same DTC concept can be extended in case of the SRM. That is a new concept, and we are working on it. We are quite successful. We have communicated a paper. However, since it is in a communication state, I cannot discuss it in a great extent. The positions is independent of the excitation. That is quite another aspect is that it can go above the base speed very well. Only thing that it will require to magnetize and demagnetize very fast. So you require to have ultimately it is a power electronics to take care of it. So if you can magnetize and remagnetize in a reverse direction, it will rotate fast. So this is the hysteresis based controller. You got IBICIC. This is the current control based SRM, and you have a hysteresis loop. Unfortunately, if you have a hysteresis controller, you know that it is not a constant frequency operation, since you know that there's two kinds of hysteresis. One is the algebraic hysteresis and the proportional hysteresis. We require to make a algebraic hysteresis so that it is if you say that it is 1% band, since the current at 0, it is actually causing that 0, that band, and with 1%, it gives you a higher band. So the oscillation will be more at the peak, and it will give us notches at the 0 crossing. So for this reason, we require to go for the parallel hysteresis band or the algebraic hysteresis band. Now, that is, I was telling you that I just throw some light on the direct torque control of the SRM. That is highly possible now, and we will show some details what should be the change of it. So we got a hysteresis controller. However, we have to estimate the same concept that you use from the DTC in PMSM or the induction machine. You have to take it from the voltage and current. You estimate the flux. Since it is already available, we have already built in. So put it there, as simple as that. If you are stimulating in an FPGA environment, so then you convert into the ABC to the alpha beta frame, and thereafter you get a selections of the sectors, and thus you got a proposed switch. You got a ABC, you have a torque ripple and the flux ripple instead of I, and that gives you the DTC of the SRM. So this has an advantage, and we have observed that we have considerably reduced the torque ripple, and it can go to the higher base, to the base speed, and other advantage can be captured in. So ultimately, now I close to yesterday's discussions. I try to finish as soon as possible. So anyway, so these some limitations with the EVs are the social problems. So that social acceptance. No, if you want to purchase it, everyone will say, where is the infrastructure? There's a significant charging stations, and whether we can go for the weekend tour. Those are the issues that we face. A technical problem, ultimately social problem, totally linked with the technical problem. Limited range. You know that once we have filled in the tank, we can go 500 kilometers. And then long charging period, there's a different model that I'm going to discuss into my next presentations. All will be captured into the next presentation. Now, impact. So that will be also discussed in detail into the next presentation. That is impact on the grid. It can be advantageous also. It can integrate the renewable energy, because please understand that if you have a coal-fired thermal power plant, if you are charging EV, you are not saving any greenhouse gases. Carbon emissions from the coal is higher than the diesel or petrol. So we require to integrate the renewable energies. And the voltage sustainability, increased peak power demand also will be a problem if you not properly manage, but it may not be so. Since you are using the power electronics, you have to live with the harmonics, and thus you have to find solution with that. Thereafter, charging, discharging, if you are doing huge power losses will take place and efficiency will be there. efficiency will be an issue. And thereafter, impact is positive is a lower operating cost is one of the advantage of this car. So charging takes just only 25 to 30 paise if you have a homemade charger. You are charging with a single phase, and also it will it will generate infrastructure, and if infrastructure is generated, definitely it will provide the employability and all those social impacts will be there. And this is the overview of it, and which I'll capture better in our next presentations. I thus, conclude the yesterday's presentations a little fast, and now I'll take the next presentations. Okay. I take questions after this second presentations. It's okay?
Yes, sir.
Okay. Give me a minute. Okay. Is it visible?
Yes, sir.
Okay. Just a minute. Just I take this small amount of water. 1 minute. Okay, so we'll start our next sessions. So that this should be our students' presentations. Now this is the EV infrastructures for the urban India. Now this is a very big challenge. Now whatever I try to capture in last few slides. So why we are not buying the electric vehicles, and if you are not forced to, like in Delhi, people have the one car, and anytime odd and even number can be introduced, they're little afraid. So for this reason, they are buying it. So otherwise, what happened? They know that they cannot bring out a car every day, and thus they wanted to have another vehicle as an electric vehicle. Then generally they use it once they have an odd number. Let's say consider that they have an odd number. So they will start that odd number own petrol vehicle. Whenever they find that there's a event day and his vehicle is odd for this reason, and he will subsequently use less. But it should be the reverse. So operating cost of this electric vehicle is less, so he should use more for earning the money back. What prevents him or that person is that limited infrastructures of the mobility in India. So let's start. So this is something, please see that why we require to have electric vehicles. You can see that indirect emissions from the electricity generations. This is the topmost one, and other is that 71% comes out from the IC engine. As I mentioned, that IC engine doesn't generate petrol. Of course, will have a less carbon footprint than the coal. But what happened, that only single person may be traveling in a car, and you can see that metros, how many people are actually carrying together. So in that way, this volume is extremely high and extremely cause of concern for the greenhouse effect. Like I am in Kolkata right now, everyone says that after 50 years, this city will be grounded, will be drowned by the water due to the warming. So there, these are the data. I don't have much time to elaborate, and this is quite self-explanatory also. And I am just going to the next slides. So, this is the, you can see that how the power consumption pattern changes. Gasoline, almost even little bit increased because of the socio-economical criteria in the developing countries increasing, because, I cannot afford car at 2000, but I can afford a car in 2015. So that is also an issue, because, salary of the Indian context increases, but the car prices doesn't increase that much. You got a diesel, you can see that since economical activity has picked up, diesel consumption has picked up. Fuel, jet fuels, because more and more people are using avionics, that has picked up. And electricity, it almost remains stagnant, it has not increased that much. But you are coming, the contribution that was quite less significant in 2000 is coming in a get extended, that is the other fuel, ethanol, biodiesel, LPG, etc., etc. Now, we have to define what is electric locomotive. We have many locomotives. You start from the e-rickshaw, you got a battery-driven trolleys. Thereafter, you got a electric buses, and you got a grid-connected rapid transport system, that is metros. So we require to define that different kind of electric vehicles. And increasing demand of the fossil fuels are the major issues. And frankly speaking, that is not the issue now. It was an issue when it was started. Till 1920, there was a golden era of the electric vehicles. Then, IC engine became a mode of transport because of the invention of the this petroleums. And thus what happened, that focus shifted. And, it is regained its, again, the position now. So what happened, it was first thrust on the electric vehicles, and the personal vehicle comes into the picture when when actually the world sees the problem of the political problem in Israel. And thus Arab decided not to sell the oil to the USA and other allied. So from there, the problem started, and then we wanted a parallel transport system based on the electricity. Now, this is one of the examples of the datas, what kind of power you require. You can see that now electric vehicle, that is e-rickshaw, is very popular. E-rickshaw is very popular, and thus, that contributes a huge amount of the electricity. That is less than 2 kilowatt. Thereafter, you got a car, jeep, taxis. This is the personalized transport which I talk about. That only the 14% of it. And thereafter, you got a 8% of it. That is freight vehicles. That is quite less in numbers. And thereafter, you got buses. And that is very much less significant. We require to have a urban transport based on the battery buses. So this is the case. We are not oil producing countries, and we require to depend highly on the oils. So 85% of our consumption has been imported. So and if in futures, and will gives you the energy independence. So that is one. Second point is quite important. The India's vehicle difference from that point of the world is 79% of the two vehicles, 50% of the auto e-rickshaw, and 3% buses, and 12% economic cars, and only 2% of the premium cars comes into the picture. Since we also, so the rich generally drive, always the driver of the economy are the richest. So you can see that they are still aloof from these electric vehicles. And this is the data I show you. This is the projected cost, that the battery, lithium-ion battery will subject it to. Like, every time, you go see that it is jumping down like anything. So ultimately, we'll see that cost of the electric vehicle also will come down. Till now, I was talking with the Tata Motor. They are saying that, in a bill of material, around 30% cost comes from the battery. So that considerable reductions in the 10% reductions in 30%, that means 3% savings of the total prices. Around 10% saving of the total prices. So, you can see that futures of the EV vehicle cells that has been projected, and this data is from the 2017. We are based on that, they have projected car will have that 20% increase and 30% increase, and the number of cars, you can see that you will have the 4.22 by 2030. And so it is the LB and the SB segment, and buses, because it has been assumed that more people will use the buses, but it does not happening. That is also a very great challenge. What we want essentially, it is not that poor will have a car, rather rich will use the public transport system so that you reduce the carbon footprint. That is the whole idea, and India has to work heavily on it. Wait a minute. Wait a minute. Sorry, I'm presenting now again. Okay, I was here. So now vehicles and the demand generation, that is e-rickshaw and auto rickshaw, we generally go for the battery swapping. But the battery swapping has a challenge because you give a discharge battery and we take a charge battery, but it depends on the number of cycles. So we require some mechanism to point it out that how many cycles it has been charged. So whether we are replacing 100 cycles charge battery with the 200 cycle charge battery is acceptable or not. So that mechanism we require to fix it up for the battery swapping mechanism, and that can be very fast. And there are the two-wheelers with the renewable energy swapping battery, and that is going to be launched in 2020, hopefully. So because of the corona, it has got deferred. So hopefully in the next year, we can see that. And thereafter, four-wheeler battery swap to be ready by 6 months. So that is something also we are looking for it, so that we can go by this kind of recharging or refurbishing the battery. Another aspect is that for the buses, being deployed with the first charger requires 100 hours charging for 100 kilometers. So that is something we require to work on it, and whether we can do it fast or not. Because car travels 100 kilometers, it can be a city limit. So I don't know about the Pune, but in Kolkata it is quite sufficient. So you run for the 100 kilometers charge. It can be a 2 trips, and so thereafter you charge it for 1 hour. Then again you start the battery. So the battery swapping can end the trip in the city. So, but we require around 6 to 9 month time, and thereafter charges at the affordable cost. I told you that cost of the charging is less, but what happened, investment is quite high. Like battery also, we are looking for the reductions of the cost of the charging, like AC charging, ready affordable single charger. Now for the without power, I don't think it has a power quality part has been incorporated. That is below 5,000. But we require to incorporate now. Till now, we don't have that kind of mechanism to monitor it. So soon that power quality will be an issue, and that cost will go high. Then there is a DC first charging of the 15 kV, and the product is about, the cost is around 1.25 lakhs in volume. So if you have a single purchase, I am not aware of the cost. So fast charging with a higher power cost largest car, so you require to make it affordable. So that cost also comes out to be that region. So capital cost of this electric charger still is quite high. So that we require to build with the cheaper alternatives. That is, though it will cost, definitely will. One of the problem is that the cost of the patents. Very few companies are doing it. So once we have starting the local manufacturing, so then the cost will go down, like mobile. So in 2030, the India could see anywhere 2000 around 100 to 30 million electric vehicles. That means it is quite large in number based on the technology and the policy. And about 85% of this will be a private vehicle. But that is something, it annoys me, because we should encourage the people to take the public transport system. And with two-wheelers making about the 70% of the mix pack, because ultimately you're putting everything on the road will be highly congested. The fleet vehicles such as taxi, buses, and the three-wheelers will make up around 15% of the EV populations in 2030. And based on that, these are all informative data, so there is not much technology. We'll share it. You can go through it. And so this is another data that is the, you can see that these are abbreviations. So it is the BEV stands for the battery electric vehicle. HEV stands for the hybrid electric vehicles. And these are the different colors. You can see that this is a LB, that is low power electric vehicles. It can be the sedan type of car. If you have SUVs and all, these will be the UB. In India, though, we classify as a car below 4 meter and above 4 meter. So you can take it something like that. So this is the LB and UB. And this
Hello, Bhattacharya sir. Are you there? Hello, sir.
I think that, madam, again there is connectivity problem.
Yes, we are calling him. I think
Huh.
there is something network issue must be
Yeah,
there.
yeah. You try to call him. It's better.
Yes, ma'am.
Participants, please wait. I communicated to sir. He will rejoin.
Your PPT is visible, sir. You are not audible.
Now audible?
Yes, sir.
Sorry. Okay. So I go to the slides where I have left it. Now I was missing from this slide, right?
Yes, sir.
Okay, fine. Sorry. So so you can see that uh, how we are planning to scale up the electric vehicles cells. Now we have a missions that is called the National Electricity Mobility. All the data has been taken from there. So we wanted to have a electricity utilizations factor conventional goal lead about 20%. So that is quite important. Let us understand what is it. The capacity utilization factor of the conventional gate load is about 20%. That means you will consumption when, because you will require to flatten our load curve. We have a peak efficiency. We don't have average efficiencies. So what happened, so when you have a non-peak time, what example my previous speakers were telling, I can put my car into the office. So then we can charge it. And ultimately, if somewhere that power demands comes and I find that it is quite attractive, I can sell that power. So that, it is a small amount of power maybe, still I can sell it. And thus you can have a better power quality management. And when you find that there's a plenty of power, you charge the power. So in that kind of concept, it is a future scope for the electric grid for this EV charging. Now, come to the India strategy, given the constraint and opportunity discussed previously, we require to have the energy efficiency for the electric vehicle charging and also, conversion. So for this reason, regenerative braking is must. We want that, that battery to be operated at a very high frequency, very efficiencies, and adding battery and the swapping options, we have to get the proper mechanism. If you have a swapping option, then we require to have a pricing that comes into the pictures. If someone gives the older battery and takes a newer battery, how it can be, it has to be factored into the pricing. So an end-to-end battery ecosystem and the material management has to be packed in, because I was talking about the recyclability of the batteries. So that is quite important. So, otherwise we already dumped lead, now we'll dump the other material. So now how to enhance the efficiency? And so one of the way is to focus on the minimized use of the energy per kilometer hour to travel. That is by using the better efficient machines, by regenerative braking. As I told you, that 30% energy has been costs in the heat because of the other because of this braking. It converted to the unuseful heat. For example, it consumed 80 watt hour per kilometer to Indian road in early 70s because it was considered excessive. The goal estimate to consumption to 45 kilowatt per kilometer. What we wanted to do, mind it is not kilowatt hour, it is watt hour. Okay, so we require to reduce it to the 45. That is our target, and that should be done by the regenerative braking. It then appears to be an impossible task, but that's what I was saying. That then I'm coming to gradually the technical part of it. The brushless DC motors or the switch reluctance motor required to be replaced by the induction motor, and we can achieve this target. And battery swapping, I was telling repeatedly, so that model has some problem of pricing, but it requires a fast charging several times in a day, and a low cost battery used could not be charged fully in less than an hour. And for this reason, this mechanism is quite acceptable for the EV, let's say for the e-Rishka and other methods. Now, this is the example of the swapping batteries. One battery is taking up the 3 wheels, and a charger used for this modular and swappable for the small batteries. And that can be a business locally, so you swap it and take it. Now, target is definitely the higher efficiency. It is watt hour per kilometers or kilometers per liter of the petrol reduces the battery size. Since I was telling you that, we require to see that the range of 100 kilometers or some kind of rate, and weight and the cost is also get reduced. For e-autos, it has to be reduced from 70 to 80 to 45 to 50. And you have a target for the e-buses to be 600 to 900. So this is quite challenging task. So how you do that? So, it is around 30 to 40% reductions. One aspect is that split battery into the smaller size, and 1/3 is swappable. So you can swap part of it and keep remaining to the other once you can charge it, so that emergency situation doesn't arise. And we require to maintain another aspect is the battery life. Battery life severely affected by the first charging at 45 degrees centigrade. Swapped battery can be charged in conditioned environment and in 2 hours of the maximized life. So another aspect is that it gives you the separate business, vehicle business and energy business, Capital cost similar to the petrol and the diesel vehicles. Operational cost same as the petrol diesel vehicles, but with no subsidy, but with a low GST. For strictly speaking, these are the government policies that has to be looked after to boost after these sectors. Another is that electricity mobility in India. The one aspect is that India opted for the MC graphite, that is the Paris Convention. We generally popularly call it as the cell of choice, and when to build the battery ecosystems. So that is the part of our treaty, so that all the signatory will help each other to build that ecosystem. And the battery packs development, that is the thermal design, that is quite challenging. So that's what it has to sustain the coalition. It has to sustain the abusement. That the mechanical design, and holistically it is a battery management system. So some speaker will speak in detail. I will touch upon it. So, and the established and the startup is actually 30 to 5%, and cell to pack manufacturing 17%, and some companies that will offer, and cell manufacturing in 2019 that has been increased to 20. And India has, unfortunately, that is also a challenge. That is lithium, magnesium, cobalt battery recycling. And one of the advantages is that 95% of the lithium-ion batteries are recyclable. And 90% of the graphite is recyclable. And we are now looking for, that is something we have some my colleagues, those who are working with the battery material, was telling that the sodium batteries, so because we have plenty of sodium, so that's still not stable. If it is stable, then it will be a great outbreak for Indian conditionality. So battery development, JV with the external ties up, and we'll have the 30% value, and that is something that a business model that we are looking for. And battery material development, is a great progress I can see. If you come to our campus sometime, we'll show that we have a dedicated schools for the battery management system. So, and the battery material development. So we are working on it to finding the battery that is suitable for the Indian conditionalities. So that, because, you have to maintain some degree of centigrade. If you import battery from the Germany, they will fit for their conditions. So ultimately, we require to have a localized designing. So this is something that we wanted to talk about in detail. This is mainly, I'm talking about lithium-ion chemistry. This is quite phenomena, and thereafter, I was telling you, yes, I don't know you are able to listen or not, that energy density and the safety are the two contradictory entities. If you increase the safety, that it will be less abusement free, but then you will find that your energy density has decreased. So this is the curve. It doesn't require much explanation because I have to cover another 30 slides. So you can go through it. Now lithium-ion battery is used uses the lithium, cobalt, manganese, nickel, graphite. So nickels also have a great problem of getting it, since it is it is said that it is a strategic materials, because it cannot be purchased like anything. We have to have a treaty, then only you can purchase it. So India does not have much of the mining of this. Import bills could skyrocket, and if you want to import the materials, that's what I was saying. So in India may need, so we are importing the oils, now we will be importing those minerals. So ultimately you are from the frying pan to the boiling water. So it doesn't save either. So focus on the recycling of the battery is one of the area that we require to go for it. And so we have a lot of startup and encourages to go for this, recovering 90% of the lithium ion, the cobalt, and the 93% of this batteries. And we require the R&D to set up a large number of recycling plant with a zero fault efficient or fault fluent. And India could import used batteries and become that hub for recycling. that Japan's and other countries are doing it quite successfully, and that model can be incorporated here. So some companies that working on the electric vehicles are Ashok Leyland, Tata Motors, Mahindra Electric, Bajaj, Kinetic, etc. And lithium-ion recycling has been started by this Excite, Amar Raza, and all those companies. And thereafter, ESOs, this is the ESL infrastructure. These are working on the making the infrastructures for this electric vehicle mobility. So this graph, this actual tables is, of course, it is a pictorial representation. Many companies are doing it. It is not if someone is missed, so don't get disappointed. It is my less ability to find it out. And thereafter, you got a chargers and the motors. These are the companies that are working on it to build a better ecosystem for India. Now, electrifying the mobility in India is one of the greatest challenge. The country has to begin to recycle the existing battery, mastering recovery of 90 to 95% such material used for the battery in the environmental friendly environment with the zero affluence level. So that is something is quite important. Now, battery dominates the cost of the electric vehicle. I told you, actually 30% cost of the electric vehicles is the battery. Sorry, it is not the cost. Rather, we pay a huge taxes on buying car. That's a different issue. It's not the cost. It's rather bill of materials. So the Tesla used the battery with the 450 kilometers range. So that is quite phenomenal. Because you charge you full your car, you expect that you will go by around 500 kilometers. So that expectation you can achieve by this Tesla. But of course, the affordability is a very big question mark. And I have shown you the few slides previously. Indian urban doesn't purchase those costly electric vehicles. And the use of the public fast charger is also a challenge. The waiting time, public charging infrastructure takes an hour for charge facility. Fast chargers, around 15 to 20 minutes, needs expensive batteries, and life is actually generally is affected also if the temperature crosses the higher temperature, and it is highly feasible that in Delhi and other cities where there's a huge population, and of course they will have it, and in summer this temperature is close to 40 degrees, and thus they will degrade the lifespan of the battery. And suppose if we have a small low cost battery with limited built-in charge, if it is affordable, so then for example 100 kilometer 50 kilometer range of the e-car scooter enough for the cities for the 90% or the 90% of the day. So how much we travel each day? So it is not very long distance most of the time. So we can manage with the 100 kilometer. So use only the nighttime slow charging, and thus you can increase the better battery life. And when no one needs to drive longer distance, 10% of the days, so what you can do that range extender battery to overcome the range extension. The swap is the second option, that is 30% battery you can swap, and thus you can go till 300 or the 400 kilometers. So that kind of ecosystem we can feature it in. And it is important for the customer not be able to charge the swapping battery themselves instead, because it is difficult. For this reason, we require to the manpower to be involved. And these are the national missions. You can see that NAB, National Automotive Board, and that thereafter there's an apex board called the National Board of Electric Mobility, and we have also the National Council of the Mobility. So these are headed by the Ministry of the Transport, and they are making the policies for the urban infrastructures mainly. Now, the India's task, the most energy efficient vehicles, that is the what we want, low uh, watt hour per kilometer will reduce the size and the cost of the battery. So thus we go for the better motor. Better motor and the driver power electronics and all those issues will, and better aerodynamics designs, etc., will increase the autonomy, we say, of the battery. The battery ecosystem packs manufacture of the 30%, cell making 30%, materials and the chemicals basically the 40%. This is the cost makeup of the balance of the system. Charging and the swapping infrastructure and the race extensions, we can use it, and slow charging and fast charging battery for the swapping. So fast charging battery can be used for the charging, and the slow battery charging can be used for the swapping. That can be done.
Hello, sir. Hello, Bhattacharya sir. Are you there? Okay, wait a minute. I will communicate to him.
Yes.
Yes, sir. You are not audible.
Okay.
I think he again left the meeting. Wait a minute. He is trying.
Okay. Am I audible right now?
Yes, sir.
I don't know what is the problem here. It is. Sorry for the inconvenience. Anyway, so you can see it?
Yes, sir.
Okay. So let us go to the sliding mode. Okay. Have I left it this place? Hello?
Yes, sir.
Okay, fine. So this is the example of the e-Rishka and the normal auto. Then we'll go into the comparison of it. It's very irritating, missing some important times for you. I totally. Anyway, so these are the parameters and the efficiency. You can see that, there can be a high, that is IC engine based vehicles, and that is the hybrid vehicles and the electric vehicles.
I think again we are facing the same problem. Hello, sir. Are you there?
Tuzapurkar madam,
Yes, ma'am.
there may be connectivity problem. Again, he left the meeting.
Hello, sir.
Yes, yes.
Yes, you are audible.
Fine. Just a minute. Let me share again. I don't know why. What is up? Is it a system problem? What this problem? I just came in my city and the network is okay. So I was here.
Yes, sir.
So you can see that efficiencies and that of the different kind of system. So and ultimately the average speed, top speed, etc. So electric vehicle has to cope up that speed. Top speed it cannot be more than 100 kilometers. So if you are putting huge amount of money, they can expect that top speed is a challenge. And accelerator also. Accelerations, you can go to the many car advertises the 0 to 100 kilometer in 10 seconds. So that is, here it is achievable. So that ultra capacitor and all those issues, whatever technology is available where you can score and doesn't score. And average cost, you can find it out in that range, So ultimately, we have what I can say that we have a case for the electricity. Now, this is the case of the electric missions of mobility. So you can see that electric vehicles, of 24 kilowatt hour, these are the numbers, how it is increasing. And this is a hybrid electric vehicle. It is not at all increasing, and we are not focusing it also. Our focus is totally the hybrid electric vehicle. Our focus is for the battery electric vehicle. Now, another aspect is that the cost challenge. In India is generally a battery cost is approximately, that's what I was saying, that 0.32 to 3.35 million, which is around 40 to 60% of the total cost of the manufacturing vehicle, I mean bill of materials and others. An excessive cost of the battery is due to the import cost, and it is not bulk production in the lithium-ion batteries in India. And India also imposes quite huge tariff on those batteries. So that has to be looked into the policy matters. Also, the lithium is a natural sources is limited amount, which will be contributed to the skyrocketing price globally soon, if we are all going towards the battery vehicles. And research is going globally to increase it. And that's what I was saying, that target is to reduce the cost of the battery, that prices is given. Technology penetrator, so these are the development of the electricity mobility. We have something called the technology penetration per cell, projected and the historical total vehicles cells, annual distance travels, mileage, based on that, the fuel consumptions. So these are the some mobilities, and the retrofitting of the electric vehicle. From there, we can get the conclusion. Now, why power electronics is key to this, all the policies. Till now, whatever I discussed, these are all informations and less technology. Now we are actually talking about the technology. So we need the motor controller, two-wheelers, three-wheelers, small and medium, large-scale buses, etc. And we require those electric vehicles. Testing facility and the skill development, that is also something that we require to develop, because I was telling it that we have a IC engine ecosystem. We can get the garage in every nook and corner of any urban cities, but that mechanism is absent. That technicians is absent. We require to have those technicians to be built. So 1 kilowatt to 300 kilowatt charger, maintenance, repairing, all those etc. has to be done. So bulk charger for the multiple batteries and the multiple cooling batteries. locked smart battery protocol to ensure that charging and discharging is fast. And now these are the some capabilities for the an analysis of the developing this ecosystem. Four-wheelers, low to moderate, two-wheelers is high, buses is moderate, and LCV is low. And price, and they are you can see that investment, that is something is very important aspect. Significant investment required to make the OEMs for the four-wheelers, and others are less. So to have these garages, we require to have a very good amount of investment, and that the investor should be agree to put the money to it. Now, of course, how this will work? Of course, it is just a case of the chicken and egg. Who is fast is difficult to say. Let's start from the government policies, subsidies, government purchase, and the mandates. Thereafter, government policies, incentives, OEMs, and the government interest will start that infrastructure for this. You can see that all the infrastructure companies I have listed, there is not much private companies. We are required to take the private money into the system so that we can have a better services and all. And we require to collaborations. We require collaborate with the industry and the consortium, etc., to awareness program so that people can buy and encourage to buy the electric vehicle. India needs to innovate an approach for it. And time of the issue is that several industries and startups have worked hard for the last few years. That is one of the silver lining, and they need to encourage to see the continuous forward development. And Make in India and Startup India, those are the program you can look at it. Now, global hybrid electric vehicle market, or in India, we'll talk about that EV market. Case for charge wide alternative powertrains for the EVs and the global demand policies. Thereafter, we got this India's EV market. So you can see that what are the gap between these two. Consumer acceptability also a challenge. Detail consumers research insights, why they are not going for it and what they require. Those aspects we have to see that, and we have to meet that gap. Production capability, that is sales. If I want a car tomorrow, whether it is deliverable, if I want, they ask that you come after 3 months, you advance the money. Of course, I won't be interested in. And price versus performance, battery price evaluations and performance evaluations. Then technological capability, more and more people, if you use it, then of course that price will come down. And ultimately the recommendation and intervention. You can see that policy framework to unlock the EV potentials, demand, incentives, supply, R&D, infrastructures, cost benefit analysis, and all those aspects come into the picture. That is the way we require to study and understand the ecosystem of the Indian scenario. Now, if someone wanted to start research or industry on it, many companies approaches me to set up this charger facility because it is a booming market. So ultimately, we have seen that this is a way to grow forward. Licensing, analyzing, we can have a license with the ABB, you can get a manufacturing because ABB may not be able to sell it. So you get the license for the local manufacturing. If you have a price, then you actually buy out a company in USA, a small company, so that ultimately you can start producing here, maybe joint venture. But I personally want that in-house R&D definitely will help instead of going for this way. Now, strength of the EV that you all know, that zero emission, quietness, smooth acceleration, reduced energy cost of the electricity. And what are the social issues? The extension of the range, extended watt-hour operation, universal design, that means super low or floor, etc. Because you have to see that all the men can be fit into it. And then the affinity with the infrastructures, next gen trucks, buses, even dumper, we want that to be electric vehicles. So these are the roadblocks for the penetrations. One aspect is that, the first point, indecisiveness regarding sustainability credentials and the new breakthrough technologies. Those technologies include regenerative braking, route selections, and the state of charge. So that is quite important nowadays. And they believe at the high initial investment that, there should be, the investor should have a confidence that, we can put money to it and we can get that money back by investing it. And range anxiety is the highest anxiety. We want that, 100 kilometer, what will happen? But, hardly you need 100 kilometer 90% of the time. So, so that assurance has to be there. So now, research and development, there's a battery. You can see that this is for the EV. How does it work? You got a battery, you got an inverter, thereafter you got a transmitter, and for this hybrid electric vehicles or the fossil fuel based electric vehicle, that is the futuristics one, to increase the length of the electric vehicle. We can have a fossil fuel, but it has to have a fuel cell stacks, hydrogen tank, etc. So that may be feasible for the buses. I don't see much feasibility of the because you don't have much constraint on the space on the buses. So that oil tank can be replaced by the fossil fuel, that is this fuel stacks, hydrogen tank, etc. with the proper protection, and thus you can have an increasing range with this fossil fuel based with this electric vehicle. Now, research and development in this sector are drivetrain motor controller and the motor DC to DC converter for the battery chargers and the battery swapping systems, electrically driven power steering, power brakes, and the air conditioning. These are something you require to work for it. And battery packs, battery cell, battery materials, we require to see that all are recyclable or not. So then we can use that cost like that. Material for the light vehicles, that is also something that quite important. So we are required to have a search for the lighter battery vehicles with the greater power densities and materials for the better insulations to reduce the heat load, and battery tires so we require everything with the more efficient, like better aerodynamics, better efficiency on every part of the system. Now, vehicle controller software integration and future technology will be definitely hydrogen fuel cell, battery chemistry handling the 55 degrees centigrade, and grid integrations. These are the way. So we got an electrode that is more economic, more environmentally friendly. We got a cells, we got a module with the integrated battery management systems, and we got a battery packs. So you know what you want to replace. So we got all those entities. So some can be swappable, some may not be swappable. You can choose one of it and fit to it and swap it if required. So these are the cell voltage and the temperature monitoring that is come to the battery monitoring system little bit. So you can see that this is a voltage of the lithium ion cell if it is fully charged. So ultimately it will gives you little above 3.8 volt, and gradually how it is decreasing while driving. I'm giving you the x-axis of time. So it is you start little close to 3 p.m. and thus we have drive the 1 hour. You can see that how the cell power has been decreased, and you can see that how the temperature has been increased, and with a normal air cooling one, of course you have a better cooling, so that it is a 1 hour of journey. If you have drive at a speed of the 40 kilometer, you have traveled 40 kilometer. Now battery cell is value is the priority should be given 50 to 70%. And battery management system that comes into the picture, that is a priority 2. And the power electronics, that is a priority 3. And thereafter, motor, it requires a very less maintenance. It requires a priority 4. And the transmission systems and the hybrid system, if you have, the priority 5. Based on that, you will design that ecosystem. And accordingly, you have to check, maybe there can be a software that will check the every cell, there is a short or not. So while starting, it will do the diagnostics. And maybe in a week, you run the battery management system, the whole packs. Thereafter, maybe in a month, you actually go for the checks that power electronics parts, every signals are coming, every boards are fine or not, because you use that, you use basically a vehicle that is subjected to the with a lot of vibrational load. So, and that may actually create a problem. So for this reason, we require to see those things has been taken care of. And of course, the machines doesn't get hampered a lot. So we require to see that. And please link that my previous lecture, since I've given today itself, so that what different motors require this kind of diagnostics. Now you can see that the priority of the battery cell, we may have required the OEMs, operation and maintenance, and the national level partner or the global level partner, and we require the R&D and the transmission system. So we can see that how the energy flows and all, and the battery management system, power electronics, and the motors. We already have the local vendors to do it. Now you come to the different aspects of the basic research. Basic research is that, we have to find it out the better material, and they have to apply research. The industry component will tell you that, customer is facing that problem. Ultimately, you give that solutions, So how can we have built a first chargers? How can we do the other as per the customers, that we are talking about the IoT incorporated into the system, so that in the mobile app, I can see that this is the 10 kilometer away, that charging stations is available, but I can charge within 10 minutes, whether it is what to go or some other places, because I have to travel and get it charged, something like that. So those ecosystem has to be fixed in. And, battery management system itself is a very big part of the ecosystem. So we have to build that. That power electronics, we have that UPS repairs, most of the things, what happened due to the cheaper cost, what happened, I have seen. Because no one repairs now the UPS. Once it happens, you have to put into the bin. So you cannot do it for the inverter once you have an electric vehicle. So we have to build that ecosystem. Like, something goes wrong with your car, you go and repair it. And thereafter, electric motor, that itself is a very big area of research. Everything, it takes care of everything. Basic research may be finished, but anyway, that has to be coupled with another different. For example, I am telling you, we have a challenge of the speed. Now we can have a devices that is silicon carbide based devices. So power density of the power electronics can be increased by 100 times very easily. The same power rating, same stack size, same size, little bit of cooling. One 10 kilowatt inverter can be converted into the 1 megawatt inverter. But challenge is that, so you can fit to that kind of motor. Well, what is the problem about fit? Can you overload that motor by V by F? So you just increase the V by F, thus you can go to the higher speed. So what is the challenge there? Challenge will be the eddy current, the losses, how you will actually take care of other issues will be there. So motor will be a basic fundamental research, So don't say that actually research on the motor has been finished. So and we also don't have very good designer of the motor, that also including myself. So I'm also learning to design those modern machines which can be scalable to same machine, same dimensions. Can I design that motor, 10 HP motor to the 100 HP motor, same dimension and size? So research and development are the key area here. That's what I wanted to say in detail. I don't have much time now. I require to finish. Thanks for your patience a lot. So we require to see that holistic view of all those things, and we hope that we can stimulate these new ideas and the research, and that can we work together for building the better ecosystem. Now, if you can see that we have a subgroups, we have a task group, and we have a key studies, then we have to put into the curriculum also that, so that DC to DC converter is something that covers into the power electronics. Still, we are teaching thyristors in a major chunk of the syllabus. That also we require to see, that we require to have a built-in capability for the engineers so that they also attract to the not only the IoT but also the power electronics and the machine. And these are the battery technologies available. I can show you. You can see that Excite, there's one of the oldest battery in India. There are batteries, but BMS system, they import it. They don't have other system. Amar Raja, these are the informations based on some companies. And you can see that, Bosch also have that problems. So ultimately, we require to build those ecosystems so that you got a tick of every aspect. Then only we have a better cost saving on, and you have an Indianization, and also you have better affordability to the customer because everything is inbuilt. Now, in that way, I cut short my presentation, and thus I conclude. So these are the few features that we require to incorporate. So battery management system, battery ecosystems, search of the battery material, search for the electricity alternatives are the major thrust of the electric vehicles, and also not the least that the electric motors. Thank you for your patience and in between the interruptions, and I thus conclude my talk.
If you have any questions, you can ask to sir by unmuting yourself.
Yes, you can ask me, and you can write to me also. Don't worry. I'll share these PPTs.
Okay, sir. Okay, so let's conclude the session. I would like to thank Dr. Avik Bhattacharya sir for enlightening us with his knowledge. It gave us deep insight into the topic field-oriented control and multi-level direct torque control of permanent magnet synchronous motor and hysteresis and DTC control of SRM. He also focused on current status of electrical vehicle infrastructure and electrical mobility in India and its strategies, which was very informative. In a very short time, sir, you touched so many topics.